line is about, and this whole section, is when I don't have the population characteristics. Okay. So before we go, we are going to talk about the research project. Don't want to forget. I haven't opened the exams at all. We are trying to hire some new department head right now, which is kind of important because they're my boss. So we've been kind of scrambling around doing stuff. But I'm hoping this weekend. Okay. With exam 2, it tends to be the worst one, worst scoring wise. So if you did poorly, you'll be fine. 3 and 4, you have the option to not take the multiple choice. And that's what tends to people either like the multiple choice or they don't. And so on 3 and 4, you have the option to do more of the essays, and you can just ditch the multiple choice. So, and then also you have the option to do several components and take the best out of. That makes sense. So as we get closer to the test, we'll talk about that more. But this tends to be the low point in the semester. I don't know if that's an encouraging thought or not, but it does get better. I guess it's my slogan today. All right, so single sample T. And it's going to seem like a lot of new stuff today at once, but I'm really trying to make sure it's not totally new for you. So we're going to work with T distributions instead of Z, because sometimes we don't have the population standard deviation. So we've been working under the assumption for Z here. Okay, remember this is called standard normal, because it's standardized. And so we know what the population mean is, and we know what the population standard deviation is. So mu and sigma. And then we've been estimating standard error for the distribution of samples. So this is the distribution of scores. And then what we've been doing, that's mu, or again, standard error, is estimating a distribution of means. That's that distribution bunny thing. And this is still Z. So because it has a known standard deviation, we can use that known standard deviation to estimate standard error. And remember, standard error is the denominator in our Z formula. Okay. So we've been using the sample mean minus the population mean over standard error. However, what do we do if we don't know the standard deviation? That kind of screws this whole thing. We can't get to standard error because we don't have the standard deviation. And that's actually more common. So Z, the thing that we start with, is actually probably the least likely thing for me to do, because I very often do not have the standard error. Okay. GRE, the IQ types of testing, so very standardized testing, you will, but for normal research, not a thing you're going to have. So instead we're going to use Z. I'm sorry, T rhymes with Z. The T distribution. So the T distribution is used when we don't know the population information. So we've still got a population mean. So we still have mu, but we're not really sure how big the spread is. So we sort of have a population because we expect a specific mu, but we don't know how big the spread is. So I'm kind of making a chart. So this is still the distribution of scores. If I want to estimate a distribution of means, I got to figure out something else to do to get standard error. So I don't know standard, let me write population numbers. So I don't have sigma, so I don't know what to do for sigma here. Well, the simplest solution is to just use the sample. So we're going to use our sample to estimate the population information, which is kind of what we did with standard error. All right, remembering that standard error's formula is standard deviation divided by the square root of n. Okay. So we were using the sample, the n part, to estimate. But now we're going to use the sample again. So we're going to estimate standard deviation. So we're going to switch symbols. This is SD, or S. Sometimes your book just says S. So remember, it's in Latin letters, so it's part of the sample. We're going to use that to calculate SD. Here's the cool part. The formula is still the same. So we used standard deviation over square root of n. We're still using standard deviation over square root of n. But now we have to estimate the standard deviation rather than rely on the population numbers. However, this last line is important. Because we're using a sample, the t-distribution changes based on sample size. So t is more flexible than z in a sense, because it depends on the number of people you have. And I have a picture here that'll help make this clear. But when sample size increases, the standard deviation, or the spread of t, right, this thing, approaches sigma. So what does that mean? What that implies is that as you have more people, we're getting better and better at estimating what the true population is, because we have more and more people. Right? So the more people you have, the more believable your sample is. We kind of talked about that with confidence intervals. So the spread approaches what we would expect the population to be. So we don't know what the true sigma is, but as we have more people, we can take our standard deviation and say that's probably pretty accurate. But the other cool thing about this is, I guess, I would say T and Z, what did I decide yesterday, Lauren? They're brother and sister? She's going to hide right there. Anyways, so T and Z, I guess, are brother and sister, in a sense. So as you have more people, T becomes Z. So they become equal. So with more people, T and Z become the same thing. What's that point? It's about 100 people. You don't have to know that, but FYI. So at about 100 people, these two things are approximately the same. The magic number for normality is still 30. But at about 100 people, T and Z are the same. So as we have more people, the better we can estimate the spread of T. And if we have at least 100 people, it's basically Z. So while this seems very different, in reality, the real problem is just we're only manipulating the fact that we don't have standard deviation. So here's a better picture. So which one? Purple is standard normal, right? So that's Z. The green one is with 2 people. So you see it's a lot shorter and flatter because it's more spread out. So the less people you have, the larger the spread, likely. And as you add more people, it squishes up. Now at 30 people, it's pretty close. I think 100 is when they're exactly the same. So as you add more people, T slowly becomes Z. Here's the biggest problem, though. It's not a problem. Here's the biggest thing that's going to be different. So you see how fat the tails are? Right? If we're looking for 5% in the tails, right, to come up with our cutoff scores, so our sort of finish line idea, and we're doing 5%. 5% for Z, we said, was always 1.96, 1.64, one of those things. But for T, it depends on how many people there are, because the tails are different sizes. So with T, the cutoff score changes based on the number of people. So with the reason we did a whole lot of Q norm, a moderate amount of Q norm, even though they change, I could have never showed you Q norm and said these are the 5 you need to remember. It's because when we hit T, you have to estimate it every single time. So we're going to get more practice. We're going to switch, instead of normal distributions, we're going to use T. So it's PT and QT. It makes me laugh. Right. And they work the same way. So PT goes from T-scores to P. QT goes from P values to T. And the way to remember which one's which is the first letter is the number you're trying to get to. So if you have PT, you're trying to get to P. If you have Q, you're trying to get to T. Okay, Q stands for quantile. And we'll do more of that, I promise. We're doing 3 types of t-tests, so we're going to do a lot of PT and QT. So because this comes up on the test in the homework like multiple times across the different homeworks for these chapters, so when would you use Z? When you have sigma. When would you use T? When you don't have sigma. They're opposites. So we have to have sigma to use Z. If you don't have sigma, you use T. And then a little bit we'll get into which T, because there's a couple types. Alright, so we're kind of conceptually like, okay, I don't know if I totally believe you yet, but I kind of get the idea. Yeah, so you're back, your row's nodding. Yeah, little nods. Maybe if it wasn't Friday after a test. Okay. Okay. So, a couple types of T. I'm going to erase this. Okay. So we've got our Z-scores. So we're going to use Z equals the mean minus mu over standard error. Okay. So we have to have English is a weird language, right? Yeah. So we have to have sigma. Talk in my other class about how it's probably one of the dumbest languages, and we get into why. Idioms are the worst. Okay. Okay, but back to t-test. So for a single t, okay, we're going to use the formula mean minus mu, so that doesn't change, right, over standard error, because if you don't have sigma, right, so no sigma, and it has to be one group of people. This chart keeps going. So for both of those, I only have one group of people, or one sample. Your participants might not be people, but one sample. Because I think we talked about, for the research project anyway, our participants are words, so they're not really people. But I still have to have a population mean. So I need to know what I'm comparing against. So a really good example of this type of test is, let's say I want to compare test scores across semesters. I don't know that I really have the population standard deviation for that. Like, I don't know what the true spread should be for these types of tests. Right? But I do have previous semesters that I can pretend are the population mean. So I can compare you guys against last semester as a to see if this changed across semesters by changing statistical test stuff. So we went from SPSS to R. So I would use this sample standard deviation, y'all's exam 2 standard deviation, as to get standard error, but I could treat last semester as the population mean. Okay. Dependent T. So what are we on, chapter 9? This is chapter 10 and chapter 11. We're not doing all of these today. So dependent T is where I have one sample tested twice. So I still have one group, but they are tested twice. Formula is still the same. So it's mean difference minus mu. Mean difference because I have 2 scores for people. So we subtract their scores and look and see if their scores have changed. So we create this mean difference score. So this would be if I could compare your first exam and your last exam. You are in both of those exams. I would subtract your mean difference and see if it's different from probably 0. So often there's this assumption that mu equals 0. And we're going to cover this idea a whole lot more in this chapter. So for right now, I would say just take down the chart. And once we get through these chapters, make sure this makes sense. But the main idea behind dependency is called dependent sample, because each person is tested more than once, is to see if their scores have changed across whatever the two tests are. So we might see, for example, I had a student doing a research project that was looking at 2 different types of depression tests to make sure they gave the same standardized score. So people were tested twice. She subtracted them to see if they were the same. So if they were the same, they would be 0, the subtraction. If they were different, they wouldn't be. So the big thing here is about this tested twice thing. Independent samples. Is 2 groups. So independent sample, they're independent of each other. I know these names are kind of terrible, but that's what everybody calls them. Is 2 samples, 2 groups of people tested against each other. So we would create a mean difference score, but it's group 1 minus group 2 minus mu. But mu is 0, so it drops out. So it's group 1 minus group 2. Divided by standard error. So we assume the difference between them is 0 for the null, right? There's no difference, so the subtraction is 0. Or it's not 0. They're greater, less than. Right. So this is where we're going. This is almost everything that's going to be on the next test. Okay, there's one more, and if we just want to add it just to make like your little table complete. Chapter 12 is about ANOVA. Okay. And we won't talk about the formula right now, because you guys would probably kill me. And it's 3 or more groups. That's 12. So the last thing we'll do in this section is cover ANOVAs. It stands for analysis of variance. Okay. Formulas are not worth looking at right now. And then it's 3 or more groups. And all of this is actually already on the that test table sheet that's on Blackboard. So kind of a preview for this whole next section. Excuse me. But we're going to start with single sample T. Just to kind of keep it simple. So we use single sample T when we know the population mean but not the standard deviation. So we're going to use that sample to estimate standard deviation. But we kind of was talking about a minute ago, that also means we have to use the sample to estimate the cutoff scores since the spread of the distribution isn't set. So by not having a set spread, we have the problem is like if it's really skinny, the cutoff scores squish up. If it's really fat, the cutoff scores spread out. So this would be like if NASCAR changed its finish line randomly based on the number of cars still left. That's kind of the idea. So as more cars exploded, I guess, I don't know, I don't watch a whole lot of NASCAR. But as they crash, the finish line gets further away because there's less cars in the race, so there's less competition. That's kind of the idea. So we're going to do those same 6 steps the rest of the semester. So if you aren't getting the 6-step thing, please stop and get help from somebody. And I have an example. So if you want to pull up that Word doc, do a couple of examples. And I have it like laid out all pretty. So on the test, this is what it would look like. And you have the opportunity to just write if you like to write more than type this stuff out. So this is what one of the test questions would look like. Okay. So, let's calculate back and forth. Suppose this sheriff person is going to reduce the speed of emergency response times to less than 30 minutes, which would be faster, which is the current sheriff's response time. No past records, so we don't have any standard deviations. People are too lazy to look them up. So now we're going to keep records because we're going to hold people to their promises, and then they give you the response times. So is that significantly faster, which is better, but that would be a less than test. Because we want speed times to speed up, which means their scores will be lower. So first step is still assumptions. And the nice thing is assumptions, make this a little bigger for you guys. Whoops, wrong way. Haven't changed. So they're still the same. So we are going to get to the scary code in a minute, but it's not going to be that scary, I promise. Hopefully. So is the DV scale? It's time. It's definitely scale. Okay. So time is a ratio scale. So I would say yes. Can we randomly select? In this particular example, you're like, but if I have all of the response times, I could randomly select a subset. So probably, actually. It would be better if they just use all of them, right? Although that 10 is all of them. It would be awesome if they only had 10 emergencies in a specific time frame. Right, in town we probably have 10 every 5 minutes. So we could randomly pull a subset of them and look at the times. Is it normal? No. Unlikely. So we only have 10 people, or 10 response times. So it's unlikely that's normal. That step has not changed at all. It's the exact same one. Step 2 is still creating the research in the null. So remember, if it says greater than, less than, those are going to be one-tailed tests. So one of the biggest things to make sure we're doing is that we're matching the test in step 2 that you pick to step 4. So where scores are either going to go up, they're going to go down, or they're going to be different. So our sample here is the new sheriff. We're going to compare that to the old sheriff times. And the DV is sort of time. Response, not rep. Again. Let's just do ER time. That's easier to spell. So if I look at the question, she said she's going to reduce the emergency response time to less than 30 minutes. So for my research hypothesis, I want the scores to go down because that would be a lower score, which would be better. Better times, but that means a lower score. So this has to be directly the opposite. So it could be that under her watch, then scores are greater than or equal to. So we're kind of saying we only care if the scores go down. If the scores go up, that's not good, but it would be non-significant. Our hypothesis is that they're going down. Everything else doesn't match my hypothesis. So that's step 2, and we're going to do a bunch of examples. So we'll try some of these other ones too in a minute. So 3, try to write it down here. We're really gonna get the mean and standard deviation. All right, so this is still under the new sheriff. So this is our sample. We're gonna estimate standard error. That means I also have to have n to get to standard error. And the only thing over here under population is mu. We already know that's 30 minutes. Bless you. Okay. So basically it's all heavily weighted towards the sample half because we're using the sample to estimate nearly everything. And we're just comparing it to 30 minutes. So here is something new. This is really new. This idea of degrees of freedom. I wish I had a degrees of freedom dance because maybe it would make more sense the first time you hear it. But I don't. This is part of step 4. You can list it under step 3 if you want, either one. It has to appear somewhere. So degrees of freedom is n-1, and that you should like highlight and circle and bold because it's n-1 until we get to like nearly the last chapter. So even if you don't quite get what it is, you can remember the formula. So it's n-1. And part of what we're going to do today, it's going to show you degrees of freedom as part of the R code. But you still kind of have to get what's going on for like the multiple choice type questions. So degrees of freedom conceptually is this idea of a number of things that are free to change. Do I have this written down on the next slide? Probably not. No. That's how it's used. Okay. So degrees of freedom are the number of things that are free to change. And everything else stay the same. That's like, to me, like one of the squishiest definitions. Like, what? But thinking about if I have a set number of scores, so I have 10 scores, and if I were to calculate the mean for those scores, I could change all of the other numbers except 1, this is where the -1 comes from, and it would still stay the same mean. So the idea, and it's a very conceptual idea, so this idea is like I could have other people fill in, but one person has to stay the same to keep the same mean, mathematically. So it's the number of things that I can change and keep the same mean as standard deviation. I was like, what? So sort of on the not theoretical end, it's a practical issue. So what we're going to do with that is use it for estimating standard deviation and calculating the cutoff score, because those two things are tied together, right? So the standard deviation changes the tails, the spread of the distribution, which changes where the finish line is. This would be my degrees of freedom dance. And we talked about this previously, so I'm going to go on to the next slide. As something that was kind of weird about the first couple chapters. So we did biased and unbiased standard deviation. I said we'd come back to it. There we are. So we did this biased estimator thing, and the only reason I ever teach it is because it's in the book, and it's part of the answers for the book. Instead, we're going to do the unbiased estimator. And I've said on the bottom, and the only thing different is n minus n minus 1. These are the only two parts. And this is degrees of freedom. So what we want to do is estimate the population, standard deviation, and error with our sample, but we can't get it perfect. So we're going to make the bottom number larger, which makes the whole, smaller, -1, derp, smaller, which makes the whole thing larger. You always want to overestimate standard deviation, right? Overestimate error so you don't make a type 1 mistake. I was explaining something to my graduate students the other day, and they both just stopped and looked at me, and I was like, what? What did I say? Because it was a squirrely afternoon, so who knows what had just come out of my mouth, right? And they were like, I finally get it. It was like an epiphany moment, and they're graduate students. So, you know, it's okay if you're like, I'm just going to take your word for it, Dr. B. Right. So We want to overestimate standard deviation, which is error, right? And which will then overestimate standard error, so that our answer is unbiased. And so that's why it's called the unbiased estimator. It's also n-1 because we have to estimate the mean. So there's lots of reasons why degrees of freedom is n-1, but if you want to think about it as like, I don't think I got everybody perfectly measured, so I'm going to overestimate standard deviation so that I can account for my imperfect measurement. I think that is like more the real reason why we do it. The very technical definition is it's the number of things that are allowed to change and keep the same set of scores. Now, the good thing about that, this n-1 formula thing, is that's what R does automatically. So we don't have to do any of that extra stuff. That's just what SD code does. So that makes our code a little easier. But we're going to use degrees of freedom in a couple ways. All right. So how do I get the numbers I'm looking for? There's a couple things. I forgot to add that we were going to have to do summary. So we could add that. Don't forget you can do summary. Oops, don't capitalize. Or thank you word for auto capitalizing everything, but don't. That's like from chapter 2. So it is coming back. So let me blow this up. That should be big enough. Okay, maybe one more. There we go. All right, so we have these numbers. And what you can do is just copy them, keep it open. So a lot of the times they will give you the mean and standard deviation already in the problem. Okay, they'll just give them to you and not the raw numbers. So we're going to do one both ways so you get an idea of like how to handle both directions. And it's actually probably a little easier if they don't give you the numbers because there's one less step. So we're sort of starting with the hard one. But let's save this as like data. So remember to enter data, enter numbers, we're going to use the C function for combine, concatenate. And then I'm just going to paste what I copied from Word. So as long as it has commas, should be good. And then if you run that, do this over here, you should get a number vector with 10 items. So that's how I knew how many there were. There was 10. So you have to have the data in here somehow. And then we all liked the summary function before. Whoops, I can't spell. So I'm going to do summary of my data. And remember, the good thing about that is it gives me the mean. So this is nice and normal. Look at that. The median and the mean are the same thing. Well, that means it's fairly normal when the median and the mean are close together. So it gives me min and max, but I want to use the mean. That's the sample mean. So I got that as 28. I know there are 10 people because other than just counting them, it says 1 to 10 over here, up here under values. So that makes degrees of freedom 10 minus 1, which is 9. But I don't have standard deviation. So I'm going to use SD. So none of that population stuff. This is all unbiased estimators of the data. I don't have any missing data, but it's not a bad habit to include na.rm because once we get to using real data sets, sometimes they have missing data. So my standard deviation is 3.71. So that goes back to chapter 2's code. And don't forget, these are all the lectures are on YouTube. So if you're like, I don't remember any of that, you can go back and watch them. But this is the one we just did, this greenhouse. If it was in a bigger data set, like that air quality thing, where it had multiple columns, we would want to do data set name and column name. But we're mostly going to do this part, because we're going to enter the data ourselves. So let's see if we can make it through at least step 3 here. So calculating the standard error, which they have is SM. You can also do SE, that's fine. To me that's more numeric, or not numeric, mnemonic. Is standard deviation divided by the square root of n. I think we kind of have written that down already, but it's the same formula. Instead of sigma divided by the square root of n, it's just standard deviation divided by the square root of n. Which is just whatever you calculated as SD, and remember the SQRT function is for square root. Or if you don't want to think at all, no thinking, which is a bonus for me. Oh, there's a close parenthesis missing right there. Just saw that, sorry. I'll re-upload these at the end. So we just did the SD function to get our standard deviation. Length function tells me how long something is, so how many numbers are there. You can just type 10 to, too much for you. This is square root. But if you have this formula, you don't have to think, no thinking. You can't get in wrong, because it's calculating it directly from the data that you have, unless you mistype the data. And you can't get, any of it wrong. So this thing calculates the standard deviation. This thing, length here, calculates how long, how many, so n. And square root does the square root for you. I'm going to highlight this. Okay. Or you could just take the one you have already. So let me take this. Okay. Now, is it always going to be called data? No, remember we called it data. Right. And then I want to divide by the square root of the length. So I got 1.17. Just in case you don't believe me, so I got 3.71, right? Was our standard deviation. And that's going to be divided by the square root of 10. It's 1.17. So the cool thing about doing it this way is, one, you don't have to think very hard. Right? That is the formula for all the standard errors. And it deals with the decimal issue of rounding. Okay. Yeah?
Why is it different past the 3?
On the second one?
Yeah.
Because I rounded 3.71.
Oh, okay.
Yeah. So it took the entire 6 places. And this code, remember, you'll get on the test. I don't expect you to remember this. Now, this thing, you'll still get this formula, but understanding that it's the same thing as z, that part I do expect you to get, that's sigma over square root of n, or standard deviation over square root of n. But the formulas themselves, you don't have to memorize. Okay, so we're going to stop there, and then we'll do QT next time. So save this example, because we're only halfway through it. And then we'll do the second example as well, so you can get a couple of them written down for you.